so we're going to start with number 1 here. And I'm only going to do part C because I think once you see how to do one part, you'll figure it out. And since part C is different from everyone, I won't be just giving you any of the answers. All right? But I think once you see one part of it, you'll see all of it. So I'm going to just grab this factor that they ask us to evaluate. I don't have to draw it. And I'll drop that into my how. But in my y here, this one, there really isn't much of a y, except probably realizing that, showing that you know that c represents speed of light. And then I think that's about it. Let's see. Yeah, because this is just checking, giving you practice at the mathematical side of it. So there really isn't much y here. I would realize that if your velocity is given to you in terms of c, it's sometimes easier to leave it in terms of c. Because as I mentioned the other day, I might rewrite this factor as the square root of 1 minus v over c quantity squared. Now, if you have v in terms of c, and you leave it in terms of c, your mathematics is easier than if you have it just as a normal number. Because let's take, for example, the one that I was going to do here, which is part C, which tells me minus 0.200 c. And so putting that in, so this is part C here. I do square root of 1 minus 0.200 c over c quantity squared. And the c's nicely cancel out. And I'm left with the square root of 1 minus 0.200 squared. And then I just do my mathematics. Let's see, there's my calculator. The only one that, if you don't leave in terms of C, the only one that's given to you not in terms of C is part A. And so in part A, you put in that value for V, and then you put in what the value of C is.
So,
yeah.
do that for all the other ones too.
Yeah. Well, put in the value for V and the value of C from our equation sheet. Yeah. Yeah, you just plug it in, and remember they wanted, what, at least 4 sig figs, I think they said? You got an error? Did you type in what I typed in? So that would be my answer. Oh, okay. What did I put? 0.9798. Let's see if that works. So the only difference is for the first one, you put in that value, and then you use the speed of light, which is here on your equation sheet, on the back of your rubric, is the speed of light there. Yes? All right, so we're on to number 2. And in number 2, we have Starship Enterprise just returned from a 5-year voyage. while traveling at 0.9 C. So 2.5 years out, 2.5 years back. If the report meant 5 years Earth time, how much time elapsed on the ship? If the report meant 5 years ship time, how much time passed on Earth? So, this is number 2. Really important factors to get into your Y here. First one is that the speed of light is constant in all frames of reference. That's kind of a given, but it might be good, especially if it's the first couple problems, to state that, to make sure that your reader knows that you know that. All right? And then I would state that less time passes in the moving frame of reference. And in this case, that's the Enterprise. All right, because we're taking the Earth as stationary, and the Enterprise is going away and coming back. And then, let's see, what else do we need to have in there? Probably should say that the Earth is stationary and the Enterprise moving. Yeah, you could say. But it's also good to know that the Earth is stationary. But we kind of get at that in the previous one, that less time is going to pass. So there's assumptions we can make there. Yeah, good. Yeah, lots of other ways to say that. So let's grab our equations that we're going to need. So I don't feel like redrawing. So we need the Lorentz transformation here. And we need the time here, our time relationship. And move those over here and make it smaller. Yeah, it is a good idea to store C into your calculator. I haven't done that one up here yet, but that would be good. Let's see. Yeah, I'm gonna store it in here. Yes. Yeah. Mine just happens to be orange. You have an 84, right?
Yeah.
Yeah. So I'm going to put in the value of C, which I have right here. So 2.9979245 times 10 to the 8. And then I'm going to hit the store button, which is right down here above my on button. And then I'm going to hit alpha program, which gives me the letter C. In fact, I'll turn on my key presses. And then hit enter. And now that number is stored as the letter C. So anytime I type in the letter C, it understands to think that. Yep. Yeah, alpha C. Yeah. Yeah. So now anytime you have to use that number, you just put in the letter C. Saves you a lot of typing and those possible mistakes from typing it incorrectly. So one thing to remember here is that gamma is always not equal to, is always greater than 1. And what that does here means that t is greater than t naught. So this is time on the Earth, and this is time on the Enterprise in this case. Right? So, I'm going to do part A, which says, if the report meant 5 years of Earth time, how much time elapsed on the ship? So 5 years of Earth time, that means the T is 5 years. I think they want the answer in years, right? Yeah. So I can leave it in years. Equals my gamma, which is 1 over the square root of 1 minus. Now remember, a lot of times I think of this as the square root of 1 minus b over c squared. I just kind of group it that way in my mind. I'm going to try to move this over so I don't run out of space so much. There we go. And I'm moving at what, 0.9 c? Make sure you check what yours is because it's different. So in here I'm going to put 0.9 c over c quantity squared times t naught. And I'm going to be solving for t naught. And the c's nicely just cancel out. So I'm left with 5 years times the square root of 1 minus 0.9 quantity squared equals t naught. T naught equals 5 square root 1 minus 0.9 squared. Enter. I get 2.18 years. So if 5 years has passed on Earth, if that's what they meant, then only 2.18 years have passed on the Enterprise. If you get a number that's larger, check your math, because you've made a mistake. Larger than 5. Larger than 5. Yeah, let me guess, you're 0.85 or something, or 0.86, see? And then for the second part, now it says 5 years on the Enterprise. So t is what we don't know. We have 1 over the square root 1 minus 0.9 squared. Sure. At the end of, okay. Yep. Fine. 0.9 squared, and then the 5 years. All right. All right. Back from lunch. Let's finish this one up. So let's see. And time on Earth, if it's 5 years on the ship, is 11.5 years. Alrighty. Alright, so let's look at number 3 next. And it's asking how fast would the average pion be traveling to travel 11 meters before it decays. I'm going to assume that 11 meters is in the frame of reference of the Earth. Alright? And the reason being, what we'll talk about tomorrow is the fact that not only does time dilate, but length contracts. So the pion isn't going to experience 11 meters as it travels, but in the Earth's frame of reference, 11 meters will be traveled. But the pion is only going to experience 2.60 times 10 to the minus 8 seconds. But of course, more time is going to pass in the stationary frame of reference, the Earth's frame of reference, than in the pion's frame of reference. So all of that type ideas should be here in your Y. Things like more time in Earth frame of reference than pion. 11 meters is in Earth's frame of reference. C is constant in all. Yeah, I think that's it. So, looking at equations, we need to translate from, what do they want again? Oh, they want it in terms of C. That's nice. So, in terms of equations, we're going to have to transfer from one frame of reference to another. So, it would be good to have the Lorentz transformation. We're going to look at time in one frame of reference and then in a second frame of reference. So, it'd be good to have the time relationship. But then we're also going to look at distance and time in the Earth's frame of reference, in just the Earth's frame of reference, right? So if we're in the single frame of reference, we don't have to translate between them. We can use our equations from ancient days. A really old stuff. So let's see, we need that because that relates stuff. We need our Lorentz transformation here. And we need our time equation. So, let's see. Alright, so, let's see. We know that T is always greater than T naught. So that means T is the time that passes in the Earth's frame of reference, and T naught is the time that passes in the pion's frame of reference, right? In the Earth's frame of reference, the pion is moving, and it's moving at some velocity called v, and it travels 11 meters. So in the Earth's frame of reference here, we can call d naught 0. We know it doesn't accelerate, so that goes to 0. We have 11 meters equals whatever speed the pion is going for the amount of time, and the variable in the Earth's frame of reference is t. All right? Unfortunately, that's two variables, which is not good to have one equation in two variables. But we know that t is related to t naught. All right? We know that t in the Earth's frame of reference is t naught over the square root of 1 minus v over c squared. Yes? Maybe?
Yes.
Okay. We're looking for v. We know c. We know t naught. Because that's the amount of time that passes in the pion's frame of reference. So t is actually, what is that, 2 point something? 2.60? 2.60 times 10 to the minus 8 seconds over the square root of 1 minus v over c squared. And I'm I'm going to substitute those two in together. So I'm going to end up with 11 meters equals V times 2.60 times 10 to the minus 8 seconds over square root of 1 minus V over C quantity squared. V is what I'm looking for. So I want to keep V. Actually, I'm going to do something very strange here for a second, okay? Because it asked me for what's V, what is, like, is V 0.6C or something like that? That's really writing V over C. So if I have, and this is the weird part, but it makes the math a little bit easier. Do it over here. If I've got, like, let's say 0.8C, I could write that as 0.8, if we have V equals 0.8C, I could write 0.8 equals V over C, right? This is what they're looking for me to answer in 0.8. They want 0.8 times C or 0.7 times C, whatever. So rather than solving for V here, I'm going to put this in terms of V over C. And the way I can do that is if I multiply both sides by C. So I can have, divide both sides by C. So I can have 11 meters over C equals V over C times 2.60 times 10 to the minus 8 seconds over square root of 1 minus V over C quantity squared. Now I can think of that just as one variable. It avoids putting in the value for C and then having to do it again. So when I'm going to put this now into Wolfram or my calculator. Which one would you guys prefer? Calculator? Okay. I'm going to put this into my calculator. So to get it ready for my calculator, I've got to do it so that the TI can understand it. And I'm going to work with the lowest level TI, which means it has to equal 0. So I'm going to do two things. I'm going to say V over C equals X. That's the first thing. And I'm going to have to set it equal to 0. So I'm going to get 0 equals 11 over C. Sorry, whoops. Let me start again. Negative 11 over C, because I've got to move that to the other side, plus X times 2.60 times 10 to the minus 8. Notice I'm dropping out all my units over the square root of 1 minus X squared. And I'm looking for X. Want to make sure you followed what I did. Yeah? Yeah, okay. So, let's pull up my calculator. And I'm going to go into math. And then I'm going to arrow up and go to the solver. And arrow up to put in a new equation. So I'm going to do negative, parentheses, 11 divided by, remember I stored C in my calculator, C, plus, I'm going to use a lot of brackets, X times 2.6 to the negative 8 equals divided by square root 1 minus X squared. Close. That should be my equation. use the XT zeta M key right next to the alpha key. That's like your generic variable key. I'm just looking to make sure I did everything correctly. Math, you hit the up arrow to get to the bottom of your list, and it's solver. And then hit up arrow again to get it to your point. You can either clear at that point or just make sure that, like my negative 11C, make sure you use the negative key down at the bottom, not the minus key. You'll get a syntax error if you use the minus key, right? How'd I get what? That is second, comma. Well, can I hit enter? Okay. All right, so I get back here, and it's telling me what C is, so that's good. I haven't solved it yet. I need to go down to my bound, and I need to take out, I'm using the delete button, till I can have 0, 199. I go down to my bound and get rid of that first, see how it says negative? Go over to the, yeah, delete. Character by character, to get that last sign. Hit 0 instead of that last sign. Now arrow back up. Changing the bound from 0 to that tells me, hey, I only want positive answers. It hasn't solved it yet. I need to put in a guess that's positive for X, so I'm going to put in 2. Although, I think that's going to be too high, so I'm going to put in 0.1. Yeah. What it is it's giving it a place to start from. So the closer you are to your answer, the better it'll be. And then I have to hit alpha, enter, because that, notice how the word solve is in green next to enter. So alpha solve. It works, and it tells me my answer is 0.816. If you got an error or something, let me come over and look at it. If you want to see what keys I hit, there are all the keys I hit. Let me check.